I will be discussing about time domain astronomy in the ultraviolet, optical and infrared wavebands. So, given below is the table highlighting the frequency ranges and the wavelength regions covered by the all the three wavebands, namely ultraviolet, optical and infrared bands. Now, if you talk about time domain astronomy, this basically pertains to repeated observation of an object of interest or scanning a region of the sky repeatedly. So, to do that, the basic requirements are a telescope. The light from the telescope will pass through either a filter system or a spectrograph, depending on whether you do a imaging observation or a spectroscopic observation, and finally, the images are recorded on the detector. So, if you talk of UV, the observations need to be done from space. In the case of optical, you can carry out the observations both from ground as well as from space. In IR also it is possible from both ground and space. Now, if you consider the telescope is basically a light collecting system, and this power of the telescope depends on the diameter of the mirror used in that making the telescope, and this is proportional to the square of the diameter. Suppose if you go for larger and larger aperture telescope, it increases the capability of the telescope to collect more photons, and once the telescope collects more photons, it will be able to detect fainter objects, and subsequently detecting fainter object leads to probing larger distance in the universe. This is also characterized with the resolution, which depends on the lambda and the diameter aperture of the telescope. So, for timing observations, small to medium size apertures are sufficient to carry out good quality time domain astronomy. This also depends on the brightness of the objects you are targeting. And if you talk about optical timing observations, this is affected by the attenuation of the light, and this increases towards shorter wavelength. If you consider UV timing, this can be done from space, and IR timing, it can be done from both from ground as well as from space. Now, as the optical light makes its path from the source to the atmosphere, it gets attenuated by the atmosphere, and this attenuation depends on falls under three categories. One is mainly by aerosols, the second is by molecular absorption caused by the ozone, and third is by Rayleigh scattering. So, how it happens? You can imagine the star rises in the east and moves up towards the zenith. As it is in the lower horizon, the air column the photon takes from the source to reach the observer is long, and because of this the attenuation suffered by the light is also large. However, if you observe the same star near the zenith, the air column the photon travels is less, and consequently the attenuation is less. So, how to practically measure this attenuation is that what we used to do is to track a star from the horizon towards the zenith, derive the brightness of the source, plot the brightness of the source as a function of air mass. The slope is nothing but the extinction in a specific filter. So, this is given by the famous Borges law of extinction, which is given here, and these various parameters make effects in different ways. Suppose if you talk of aerosol scattering, it depends on wavelength as well as the height of the atmosphere. Rayleigh scattering too depends on wavelength and the height of the atmosphere, whereas molecular absorption by ozone depends only on the wavelength. So, what is given on the right is the plot of the extinction versus wavelength. So, as you see from the graph, as you go towards shorter and shorter wavelength, the extinction goes up very high rapidly. On the table towards the left is given the measured extinction values for different pass bands carried out for the 2-meter telescope site in Henley. As you see, in the U band the extinction is larger compared to the I band filter. So, what is the methodology used to do time domain astronomy? So, for doing time domain astronomy, so we have to either take repeated observations of the target or scan a region of the sky repeatedly. So, this can be done in three modes. If you want to do imaging observations, you take repeated image of the sky or the target of interest, Alternatively, if you want to do spectroscopic observations, you carry out repeated or you record repeated spectrum of the source, and the same is true for polarimetric observations. So, what is shown on the right is a typical image taken from the 2-meter Himalayan Chandra telescope situated at Henley, and the image corresponds to a field of view of 10 arc minute by 10 arc minute, and the image shown at the bottom is the spectrum of the target, which is shown by red on the image. This is basically the plot of the light as a function of wavelength. It can be considered as a high resolution photometry. Alternatively, photometry can also be thought of as a low resolution spectroscopy. So, to carry out time domain astronomy, we have to have the scientific motivation clearly laid out, and once the scientific motivation is laid out, we have to choose the targets we want to monitor, whether the source is a very bright object or it is a faint target. Once the target is identified, we have to see what site is suited to carry out the observations. So, here we basically makes two decisions: what is the size of the telescope you want to carry out the observation, and what is the location of the telescope. And once these two things are identified, you have to ask whether the source you want to target is visible. So, we have to basically worry about the duration of observations. And the fifth point we have to keep in mind is what kind of instrument we use, whether we want to do imaging observations or we want to do spectroscopic observations. If you are interested in imaging observations, we have to finalize the filters we want to use, what kind of filters we want to use, whether the passband of the filters are broad or it is narrow. And if we want to deal with spectroscopic observations, we want to decide on the grating to be used as well as the slit. Once this is decided, we want to carry out we have to carry out calibration observations to put our observations on the standard measurements. So, in the case of imaging observations, we need to carry out certain calibration observations called bias observations, flat field observations, as well as we have to observe some standard source to calibrate or to measure, to bring the measurements to a standard scale. In the case of spectroscopy, we have to carry out lamp observations to put our observations on wavelength scale, as well as we have to observe some standard stars to convert our observations to standard units. So, what you do in observations? In the case of observations, we basically collect the light from the celestial source, and the light from the celestial source passes through the Earth's atmosphere. After passing through the Earth's atmosphere, it enters the telescope, it gets reflected off the mirrors, primary as well as secondary. It then passes through the filter, and finally, it gets recorded on the CCD devices, and the images or the data recorded are then used for further analysis. So, what kind of analysis we need to do to convert our measurements to useful science observations are as follows. The reason is, for the photons which we record passes through the atmosphere, and we have to correct for various effects the photons have when we record on the detector. So, some of the effects are given below, and these effects are needed to remove the effects of the instrument and the atmosphere that has on the signal. So, these effects are we are talking about is about the dark, we are talking about the bias as well as the scattered light which comes into the detector apart from the light from the celestial source. So, all these signals adds to the strength of the photons received, and so these are additive signals which have to be removed from the photons we collect from the source. The other effect which we want to remove is called flat fielding. This is due to the following reasons. The data is recorded on the CCDs. Though charge coupled devices are linear devices, there is inherent pixel to pixel sensitivity variations, and this pixel to pixel sensitivity variation has to be removed. So, for that we follow a procedure called flat fielding, wherein the telescope or the detector is exposed to a blank sky. The assumption here is that the sky is uniform, flat. So, once we record these images, these flat fields or the science frames are divided by the flat frames to bring the pixel sensitivity to a uniform level. So, once this is done, our observations are also affected by what are called cosmic ray events. So, these cosmic ray events also hit the detector and they also get recorded. So, for useful science observations, these cosmic rays also need to be removed from the actual observed data. So, once this is done, so we have what are called the clean image frames, which are devoid of all the artifacts which are on the recorded data. Now, we have what are called the clean image frames, and on these clean image frames we want to do certain procedures to convert that observations into useful data where we can do further analysis. So, in the case of imaging, this is done in two ways. One is called aperture photometry and the other is called the PSF photometry or point spread function photometry. The basic idea of aperture photometry is that suppose we are interested in knowing the flux coming from a star, what is normally done, an aperture is placed on the star of interest, all the photons within the aperture are collected and then the magnitudes are derived. And nowadays these things are done by standard softwares available. Here I mentioned few softwares such as IRAF, which is called the image reduction and analysis facility. There is another software called MIDAS, which is called Munich image data analysis system, and the third thing which I mentioned is called the source extractor. So, the problem here is that if you put an aperture around a star and collect the photons you measure is the sum of the photons coming from the sky plus some additional background photons. Basically, these background photons are sky photons. Therefore, to get the actual number of photons coming from the star, we have to remove the photons coming from the sky. So, this is done by selecting an annular region around the target of interest. The sky photons are estimated from the annular region what we select, and once the sky photons are estimated, this is subtracted from the total photons collected within the aperture. And this definition of the aperture cannot be arbitrary, because we cannot choose any aperture to collect the photons, because selecting too small aperture will lead to a condition where we are not able to pick all the photons coming from the star. Alternatively, if you choose a bigger aperture, you collect more noise photons relative to the source photons. So, the ideal aperture to choose for photometry, which is basically collecting the number of photons coming from the star, is to have an aperture which is close to the full width half maximum of the light distribution coming from the star. So, this kind of photometry, which is normally called aperture photometry, works for sources where there is not much the field must not be crowded. If the field is crowded, we will not be able to accurately determine the sky as well as do proper photometry on the stars of interest. So, what is shown on the figure is a typical case where the sky is so crowded, and finding the light photons emitted from each star on this crowded field using the usual way of aperture photometry is going to be difficult. So, for situations like this, we have a technique called point spread function photometry. Here what is done, few stars, isolated stars are selected on the field. The light distribution coming from the stars are well modeled, which is called such that the PSF is well modeled. So, once this PSF is modeled, it is applied to all the stars detected on the same frame. There are of course problem in this method, because due to the following two reasons. If the field is so crowded, the usual method of PSF photometry may have some issues. Alternatively, if the point spread function is also variable across the CCD frame where you detect the image, that time also this technique of PSO photometry may not yield correct results. Now, once you have the brightness of all the targets recorded in a suitable frame, we have to bring these observations into some standard units. This is normally achieved by performing what are called the calibration observations or standard star observations. This is done as follows: we have well defined catalogs where the brightness of stars are certain stars are well known. So, what is normally done? Using the same instrumental setup, we observe those standard stars whose brightness are well known. From that, we get transformation coefficients to convert the instrumental brightness to the standard brightness. Once this is done, we have to put our images, which is normally recorded in the xy coordinate system, to the standard world coordinate system. In astronomy, it is the alpha and declination system. For this, normally what is done, we select some stars on the observed frame where the x and y positions are known. For those same stars, the world coordinate informations are also known. So, transformations are derived between x and y coordinate system to the alpha delta coordinate system, and once this transformation is established using known stars, this is applied to all the stars in the observed image frame. So, this is how the observations we do are converted back to useful data where we can do science out of it. And one of the applications of doing timing astronomy is to find new transient sources which are coming on the sky, new sources. A source may be say below the detection limit for a large fraction of time. For some reason, if the source brightens up, and if you want to detect such transient events, such events are called transient events, we have to perform what are called differential photometry. That means, you take repeated scans of the sky, consider the first scan as the reference image and do difference image. That means, you subtract the, suppose you have ith frame and I plus 1th frame. So, what you do, you subtract the I plus 1th frame from the ith frame. If no stars are in the, no objects in the field are variable, you get a difference image which is basically the noise. If any stars on the field brightens up, that will be shown in the difference image. This is one of the ways to identify transients in the sky. So, this is about the imaging observations. Alternatively, in addition to imaging observations, people also do spectroscopic observations wherein repeated spectrum of the target of interest is taken. So, here also once the spectrum is taken, which is basically the plot of, which is basically the counts as a function of wavelength. Here wavelength means initially we record in terms of pixels. Here we need to perform two important calibrations. One is called the wavelength calibration. This is needed to convert the pixel coordinate system to wavelength coordinate system, and the second important calibration needed is to convert the photons we record into useful units in terms of flux. So, what is normally done? Standard stars are measured whose flux is well known, and by this one can calibrate the observed instrumental magnitude to the flux units. So, if you do spectroscopy, what we get? We get a series of spectra, and each spectra are recorded at different times. Given this background about spectroscopic and photometric observations, I will now move on to explain how timing observations will be useful to understand the physical properties of these sources. The first kind of object which I am taking is what is called the active galactic nuclei. So, active galactic nuclei are those sources in which the nucleus of a galaxy is active. Basically, they refer to the point sources at the center of a normal galaxy. So, we all know about normal galaxy. Galaxy is nothing but a collection of billions of stars. So, this is the case of a normal galaxy. So, apart from these normal galaxies, there are certain kinds of galaxies which are active. Active in the sense, the nucleus of the galaxy emits an enormous amount of radiation which outshines the light coming from the entire galaxy, and such a large luminosity is coming from a very small region in the center of the galaxy. And now it is known this kind of emission or enormous amount of luminosity from a small region is possible by a process of what is called accretion. Basically, a black hole sitting at the center of the galaxy accretes matter, and this powers what is called the active galaxies. So, suppose if you take normal stars, these are powered by nuclear fusion processes, wherein 4 hydrogen nuclei combine to form what is called the helium nuclei, and the radiation coming from a star, it can be explained by a Planckian law. Whereas, in the case of active galaxies, the radiation is mostly dominated by non-thermal processes, and one of the signature of some violent process happening in these active galaxies can be recognized by the presence of broad emission lines in the spectrum of these objects. Broad emission lines, I mean the emission lines having widths greater than 10,000 kilometer per second. So, such broad lines point to some violent process happening close to the central region of these sources. And yet another important property of these active galaxies are that they emit radiation over a complete range of the electromagnetic spectrum, starting from low energy radio waves to high energy gamma rays. And some fraction of active galaxies also produce large scale relativistic plasma, which can extend much further from the host galaxy, which is called relativistic jets. So, this happens in a small minority of active galaxies. And how do you identify these active galaxies? Suppose if you take a normal galaxy is nothing but a collection of millions of stars, billions of stars. And if you see the spectrum of a star, it can be well explained by a black body, wherein there is a continuum, and superposed on the continuum in the case of stars we see predominantly absorption lines. So, therefore, if you take the spectrum of a normal galaxy, the spectrum of a normal galaxy is nothing but the superposition of the spectrum of billions of stars in the same galaxy. Therefore, in the case of a normal galaxy, you expect to see a continuum, and superimposed on the continuum you see absorption lines. However, there are some normal galaxies where you do see emission lines, which mainly comes because of violent star formation process happening in them. But how to recognize a active galaxy from a normal galaxy? So, what is shown on the right are two spectrum. One spectrum has a continuum, and superposed on the continuum are absorption lines. This is the spectrum coming from a normal galaxy. What is shown on the top is the spectrum coming from an active galaxy. Here what you see, contrary to what is seen in normal galaxies, we see a continuum. Superposed on the continuum we have lots of emission lines. These emission lines are characteristics of the elements present in the object. So, what you can notice here, the width of the emission lines are very broad. They typically have widths more than 1000 kilometer per second. This is how you identify a normal galaxy, active galaxy. And if you see the energy source for active galaxies, the energy source is mainly by accretion, and this is a very efficient way of producing energy in AGN, having a efficiency of the order of 10%. So, for comparison, if you take nuclear fusion which happens in stars, the efficiency is very low, of the order of 0.7%. So, accretion, a very efficient process, is the mechanism which happens in active galaxies or active galactic nuclei, which refers to the nuclei of those galaxies. Now, I give a comparison of how the luminosity is produced by AGN compared with other objects. So, if you take the case of sun, it is around 10 power 26, whereas in the case of most luminous AGN, it is of the order of 10 power 42 joules per second. So, they are much more luminous objects. The whole field of AGN started in 1963. As time progressed, both with the advancement of technology as well as the advancements of other fields of astronomy, various kinds of AGN were identified. And if you take the population of AGN, they are basically grouped into two broad categories. A large fraction of them do not emit in the radio band, or if they emit very low emission. These objects are called radio quiet objects. They constitute a large fraction of around 85%. A minority of sources emit lots of radiation in the radio band, and this comprise around 15% of the sources. Now, if you talk of these radio loud objects, they are grouped into two categories called radio galaxies and blazars. So, blazars can be further divided into flat spectrum radio quasars and BL-like objects. If you see in the radio quiet category, we have Cepheids and quasars. So, quasars are nothing but the luminous counterparts of Cepheid galaxies, and in Cepheids they are grouped into two categories called Cepheid 1 galaxies as well as Cepheid 2 galaxies. However, all these objects are grouped into what is called the unification scheme of AGN. According to this scheme, whatever different types of AGN we see are basically the same objects. We see them differently because they are observed at different angles to the line of sight to the observer. Suppose, so in this unified model of AGN, a AGN has a central black hole, and surrounding the black hole we have what is called the accretion disk, and further out we have what is called the torus. This is the donut shaped structure in this figure, and the central dark object is what is called the black hole. So, suppose you see this galaxy from the pole, and above and below the accretion disk we see what are called the broad line region clouds. These clouds are responsible for the broad lines in the optical spectrum. Further out from the broad lines we are having what are called the narrow line clouds. So, if you see this object from the pole, you will be seeing both the broad line region as well as the narrow line region. Therefore, in the observed spectrum you will have both the broad lines and the narrow lines. This is the case of a Cepheid 1 galaxy. On the other hand, if you see the galaxy edge on, that means you are looking into the torus. In such a scenario, the broad line regions are blocked from the view to the observer, and consequently in the observed spectrum you see only the narrow lines. Such a source is called a Cepheid 2. So, there are observational evidences to support this unification model. So, what I show here is how the typical spectrum of different class of sources. I showed two sets of spectrum. On the right there are three spectrum coming from three different objects. The middle one is what is called the Cepheid 1 galaxy. That means, you are seeing the AGN pole on. In this scenario you are able to see the broad lines as well as the narrow lines. So, here the broad line what you see corresponds to H beta coming at 4861 angstrom unit, and the other two narrow lines correspond to the oxygen. The first plot on this graph you can see the H beta line as well as the oxygen lines are narrow. So, this is a scenario where you see the source edge on, where the broad line region is blocked from you. So, this is called the Cepheid 2 galaxy. On the bottom panel I show what is called the narrow line Cepheid galaxy. These kind of galaxies were known only in 1985. These galaxies are intermediate between Cepheid 1 and Cepheid 2, meaning the width of these broad lines are smaller than Cepheid 1, but larger than Cepheid 2 galaxies. On the left panel I show two plots, two spectrum. What is shown on the top is the spectrum coming from a BL-like object. So, BL-like objects are those objects where we are seeing into the jet. So, if you see into the jet, the radiation coming from the jet is beamed towards you, and because of this the continuum gets boosted and the emission lines are getting suppressed. So, in the case of BL-like objects we see either a featureless spectrum, or if lines are there they are generally weak. On the bottom panel is shown the spectrum coming from a BL-like object on a flat spectrum quasar. So, this has a continuum as well as the broad emission line. There are other class of objects which are viewed at larger angles from the line of sight. So, they are called misaligned AGN. So, if you see the radio maps, they have resolved and symmetrical structures. The spectrum, the radio spectrum are generally steep, and in terms of radio morphology, they are classified into two different categories called Fenner-Rayleigh class 1 source and Fenner-Rayleigh class 2 source. So, what is shown on the left is a typical radio image of a Fenner-Rayleigh class 1 source, and what is shown on the right is an example of a FR2 type radio source. And in the table below, I give the differences between these two categories of sources. They are mainly based on two people who made this discovery called Fenner and Rayleigh. Now, how timing observations will be useful? We will see how timing observations will be useful to understand these sources. So, what I show is a typical example of the timing data collected from a source, collected from a blazar. So, when we call blazar, it is a name given to a combination of flat spectrum quasars and BL-like objects. That means, BL-like objects and flat spectrum quasars are together called as blazars. So, what is shown on the left is the time series data collected over a period of many days over a wide range of wavelengths, starting from infrared, optical, X-rays and gamma rays. What is shown on the right is the typical spectral energy distribution emitted by a blazar. So, if you see that, you can see a two hum structure. So, one hum, the low energy hum, can be well described by a synchrotron emission process, whereas the high energy hum is explained by what is called the inverse Compton process. So, this is how the broadband spectrum of a source look like. Suppose if the physical process or if the electrons contribute, that means the electrons contributing to synchrotron process, we know how the synchrotron spectrum look like, and once we know that, we will be able to predict how the second hum of the SCD also looks like, because the second hum is basically coming from inverse Compton process. A low energy photon is Compton upscattered to higher energies. Therefore, if any variation happens in the optical or UV photons, it is expected that the X-ray as well as gamma ray photons show the same behavior in the case of leptonic models. To test whether this hypothesis is right or not, timing observations holds a very important key. One such example is shown on the left. So, here I blocked 3 shades. In the first shaded region, whenever the source shows increased brightness level in the optical IR and X-ray band, increased brightness level is also seen in the gamma ray band. Here gamma ray is in the topmost panel. Now, come to the second shaded region. Here the optical and UV brightness changed by the same amount as the first shaded region. So, in principle, you expect that the gamma ray flux also must show the same change. However, contrary to expectations, if you see the gamma ray panel, that is the topmost panel, the source is not detected in the gamma ray band. So, now coming to the third shaded region, here also the source showed increased brightness in all the wave bands starting from optical, IR, X-ray and gamma rays. Therefore, the only difference here is that is in the middle shaded portion, where one expect that since the source is showing increased brightness in optical and IR bands, it also must show increased brightness level in gamma ray band. However, it is not observed. The reason what is known from observation of this kind, or the reasons which can explain the observation what is seen here, is that there can be some enhancement in the magnetic field of the source which can cause this kind of observation. Because as we know, synchrotron power is proportional to E square B square, and therefore, any enhancement in the magnetic field can give rise to increased synchrotron emission. Subsequently, you can see increased optical and UV radiation. Alternatively, inverse Compton is independent of magnetic field. Therefore, this will not be reflected in the high energy and you may not be able to see the increased activity in the gamma ray region. So, this is one of the possible explanations given for this kind of observation. Now, we will move on to the next application of timing. So, what is shown on this is the brightness variations shown by a source within a night, say within 4 or 5 hours of observations. So, here in each plot you see 3 panels. So, I will explain what these 3 panels are. The first panel is the differential light curve, that means you take the brightness of the quasar minus the brightness of a comparison star. The second panel is again the difference in the brightness of the quasar with respect to a second comparison star, and the third panel is the difference in the brightness of 2 comparison stars. That means, if 2 comparison stars are non-variable, you see a flat light curve which is seen in the third panel, whereas in the first 2 panels it is the differential light curve with respect to a non-variable standard stars. Therefore, any variation is seen in the quasar can be easily detected by this kind of method. This is what is called differential photometry. There are certain advantages for this method compared to conventional photometry. The advantage is as follows: if there is any change in the weather or any atmospheric changes, if you do differential photometry, that gets cancelled out, because both the comparison star and the target of interest are in the same CCD frame. In such a scenario, if you do differential photometry, both these objects must have experienced the same effects and this gets cancelled out, and by this way we will be able to detect very small variations which the AGN is experiencing. So, this is also another such observation. These observations are taken from the 2-meter Himalayan Chandra telescope. The third application of timing is to find new quasars or new sources. So, what I show on the right is the image of a region of the sky taken during 2 different times. The one on the top is taken on 25th March 2011 and the one on the bottom was taken on 19th April 2014. So, one thing is very evident: a bright source which was seen on 19/04/2014 is not seen on 25/03/2011. So, what I want to point out is that this source changed by 5 magnitude in brightness. Magnitude is a measurement of brightness in the optical band. That means, this source, particular source which is in the center and marked by 2 arrows, brightened by 5 magnitude. So, in terms of flux, the source brightened by 100 times. These kind of observations are possible only when a same region of the sky is repeatedly scanned. That means, when we have timing information on this source for a long duration of time. So, since this object has brightened by 5 magnitude, it is a new target and this has to be characterized, means we want to understand what this source is and what are the properties of these sources. So, when this happened in 2014, what we did, we were very keen to know the nature of the source. So, for that, only these imaging observations are not sufficient, because we have to go for spectroscopic observations to actually find the nature of the source, whether the source is a galactic source or it is away from our galaxy. So, for this source we carried out spectroscopic observations. We also looked into the radio archives to see if this source is a radio emitter. So, what is shown on the left is the radio contour taken from the taking a radio map at 1.4 gigahertz. So, which clearly shows that this source is detected in the radio band also. Soon after this, we also did some observations in the X-ray band using the Swift optical X-ray telescope. We also did some observations using the New Star. It is a hard X-ray telescope launched in 2012, and using all these observations we plotted what is called the broadband spectral energy distribution. And if you see this distribution, we clearly see a 2-hum structure, which is a characteristic property of blazar, and this observation led to the discovery of a new gamma ray emitting source. So, the message I want to convey is that timing observations will also help you to find new sources in the sky. Yet another property of time domain astronomy is in cosmology. So, here what I want to emphasize is that Hubble constant is a very important cosmological parameter. Though this was known in 1920s by Hubble, where he found a linear relation between the recession velocity of the galaxies and the distance. He found a relation and he explained as V is equal to Hubble constant into the distance. H naught is what is called the Hubble constant. In 1920s, he arrived at a value of around 558 kilometer per second per megaparsec, and now we know it is around 75 to 100 kilometer per second per megaparsec. The task at hand is to reduce the error in this Hubble constant measurement. So, one of the ways to do this is by carrying out timing observations using the timing observations and using the method of gravitational lensing calculate Hubble constant. So, this is shown in this figure here. So, what is shown on the left is the real quasar. The light from the quasar is passing through a lens. It can be a galaxy or it can be a cluster of galaxies, and after passing through the lens it is coming to the observer. As it passes through a highly gravitating object, the light gets bent, and instead of a single quasar we see two images of the quasar. This two image system depends on the configuration of the quasar, lens as well as the observer. In the simplest case of this two image system, the light coming from these two quasars will take different paths to reach the observer. Therefore, if you monitor this quasar for a long duration of time, you measure what is called the time difference. Once you know the time difference, it is related to the Hubble constant by the following relation: delta t is nothing but 1 by h naught. It also depends on the lensing galaxy. So, if you are able to model the lensing galaxy properly, we will be able to measure what is called the Hubble constant. So, such a measurement was carried out using the 2 meter Himalayan Chandra telescope. So, what is shown on the right on the left is the image of a lensed quasar. We are seeing this is a doubly lensed quasar, wherein we are seeing two images of a quasar. What is shown on the right is after some image processing. Here some image processing is done and we are able to resolve these two quasars separately. In addition to that, we are also able to see two lensing galaxies which are marked by G1 and G2. This field was observed once in 5 days. So, this observation was continuously done once every 5 days and repeated for few years, and from this data what was done, photometry was performed on these two point sources, two lensed quasar images. Photometry means basically the photons are collected from these two objects, and this is plotted as a function of time. So, what we show here is a graph which is shown the magnitude on the y axis plotted against the time. Magnitude is nothing but a measure of brightness in optical astronomy. So, the first one graph belongs to object A and other graph belongs to object B. The light curve from object B is shifted by 119 days. That means, the photons or the time delay between images A and B is roughly 119 days. So, once we know the time delays, we will be able to calculate the Hubble constant. The other application of timing is to probe the inner structure of AGN. So, as I told you, AGN has a central supermassive black hole. It has an accretion disk given by the maroon color here, the blue color clouds which give rise to what are called the broad lines in the spectrum, and then we have a donut shaped structure called the torus. So, here based on timing observations, we will be able to find the mass of the black hole. This is a direct measurement of the mass of the black hole. How it is done is as follows: optical UV photons will come from the accretion disk. Okay. These optical photons will travel to the broadline region, and these broadline region emit what are called the broadline clouds. Therefore, if you monitor or if you take repeated spectrum of the source, you find some time delay between the continuum of the spectrum and the line emission, because the continuum is coming from the central region and the line emission is coming from the broad line clouds. So, this delay depends on the distance of the broad line cloud from the central engine. So, once we know that, we will be able to put the constraint on the black hole. So, this is what is called, this can be done by a method called spectroscopic reverberation. The other application is to find the inner edge of the dusty torus. So, how it is done? This is done by observing the source repeatedly in optical and infrared bands. The logic is as follows: optical photons, optical UV photons come from the accretion disk, they travel outwards, come to the torus, and from the torus they gets reprocessed and comes as IR. Okay. Therefore, if you monitor the source in optical and IR radiation for a long duration of time, you expect to see time delay between the optical and IR light curve. Light curve is basically a plot of flux as a function of time. So, this time delay depends on the distance of the torus from the central engine. Therefore, by repeatedly monitoring the source in spectroscopy, we will be able to find the mass of the black hole, first thing. The second thing is, if you monitor the source repeatedly in optical and IR band, you will be able to find the inner edge of the dusty torus. So, this is the way how you find the extent of the dusty torus. So, what is shown on the top on the right there are 4 light curves. So, what is shown on the second on the first bottom panel is the radiation coming from the continuum, and the second panel from the bottom is the radiation coming from the line. So, if these two time series are correlated, there are certain techniques called correlation analysis, whereas we can correlate one time series with respect to the other, and if there is perfect correlation, the correlation function peaks at 0. If there is any time delay, the correlation function peaks at a time which is different from 0. So, this is exactly shown on the left panel. So, what is done? We find that the correlation function peaks at a delay at a lag of around 3.59 days. That means, the delay between the continuum and the line emission is of the order of 4 days. So, once we know the delay, we can estimate the size of the broad line region simply by light travel time arguments, which is nothing but the size must be less than c times the time delay. So, if you apply this simple thing, we find that the size of the broad line region is of the order of 0.003 parsecs. So, this is an example of how to get the size of the dusty torus. So, what is shown on the right is the light curve coming from the V band, visual band, and 3 infrared J and H bands, and what is shown on the left is the cross correlation function between different light curves. So, from this cross correlation function analysis, we will be able to find the inner edge of the dusty torus. So, this method is what is called the dust reverberation mapping. So, as of now, we have seen how timing observations will be able to understand the physical properties of the sources, how timing observations can be useful to find new sources, how timing observations can be useful to find the mass of the black hole, how timing observations can be used to find the inner edge of the dusty torus. So, now I focus on one thing where timing observations will be used to find new AGN, because one of the defining property of AGN is variability. Therefore, if in a sky you find sources which are showing random variability, in all possibility they are likely to be AGN. So, here I show some example where a region of the sky was completely absorbed by the Sloan Digital Sky Survey. What these authors have done, they have looked for variable sources in the sky, and from variability they identified roughly some 130 new quasars in this region of the sky. So, timing observations will also be useful to find new quasars. So, what is shown on the top is the image of a typical new quasar identified by this method. What is shown on the bottom left panel is the light curve coming from this new quasar, and what is shown on the right panel is the position of the source in what is called the BPT diagram. From this diagram one can tell whether the source is an AGN or whether it is the source is powered by starburst. Yet one another area where we can where timing can play a major role is what is called the changing look AGN. This is a relatively new field where people find that AGN can transit from type 1 source to a type 2 source. Type 1 source means, I repeat, similar to Seyfert 1 galaxies, they have both broad lines and narrow lines in the spectrum. Type 2 means they have only narrow lines in the spectrum. People have recently noted that certain AGN go from type 1 to type 2 state, and there are two reasons for this. One possible reason is that there can be changes in the obscuration along the line of sight from the source to the observer. The second possible reason which is postulated is due to changes in the accretion rate. Some new advancements which have happened here is on observations on a source where people have looked into data available from what is called the Catalina real time transient survey. This is a survey of the sky which happens in the optical V band, and there is another survey called WISE survey which happens in the infrared bands. So, what is shown on the right is the optical light curve on the top panel and the infrared light curve on the bottom panel. What the authors have found? They found that the time delay between the infrared and optical bands is consistent with variation of the source happening because of accretion and not because of obscuration. So, observations of this kind will try to pose important constraints on the nature of these new kind of sources which are called changing look AGN. Now, what can we do from UV? So, till now we focused on optical and IR. By studying UV variations, we will be able to probe what happens close to the accretion disk of the source, and this UV variability is a relatively unexplored area because we have very few UV missions. As I told you, UV has to be done from space, and so these are very expensive, and I list below few examples. One is called the International Ultraviolet Explorer. This mission is no more operational. We also have the GALAX mission, and what I show on the right is the variability seen from GALAX data. GALAX surveyed the sky in two bands, one in the far ultraviolet band and the other in the near ultraviolet band. So, what is shown on the right is the light curve from a white dwarf where they have found to show variations, and what is shown on the left is the light curve from a AGN where beautiful variations are noticed in a wide range of bands from 1400 angstrom unit to roughly 3000 angstrom unit. So, this is from the mission called International Ultraviolet Explorer, and we also have what are called the SWIFT UVOT. SWIFT is a mission which is in sky. This has soft X-ray payload, hard X-ray payload as well as the UV optical payload. The last one which I list is called the Ultraviolet Imaging Telescope Onboard AstroSat. AstroSat is the Indian space mission launched by ISRO in September 2015. One of the payloads on board AstroSat is what is called the Ultraviolet Imaging Telescope. This gives enormous ability to absorb the UV sources in the sky. I briefly explain about the Ultraviolet Imaging Telescope. It is a twin telescope. We have two telescopes aligned together. Both these telescopes have a diameter of roughly 40 centimeter, and this telescope has the capability to absorb simultaneously in the visible band, far UV as well as the near UV band. And this telescope covers a field of view of roughly half a degree. This corresponds to roughly the size of the moon, and this is an ideal instrument to do timing observations, but this instrument is observing carrying out regular observations since its launch without any degradation, but timing results are expected to come soon. So, these are about timing studies on AGN. However, the same timing studies can also be used to understand other kinds of sources. So, here I list a particular kind of source called supernovae. Supernovae refers to this sudden explosive events by the stars towards the end of their phase, and this explosion produces enormous amount of energy, and in this explosion sends out much of the star's material, into the interstellar medium. Therefore, new stars born out of this enriched medium will be having metal richness, and this kind of supernova shocks can also give rise to new star formation process. And these two supernova comes under various categories. They are classified into various types called type 1A, type 1B, etc. This depends upon the features seen in their optical spectrum. The problem is these supernova are classified based on different features we see in the spectrum. However, we still do not have a clear idea of what causes these differences both in the spectral nature and in the timing nature. So, what is shown here is the light curves shown by two supernovae, one on the left is type 2P and one on the right is type 2B. As you see, the nature of the variation is completely different. So, one of the aims of these timing observations on supernovae is to understand what causes these kind of variations in these strange objects. Here again I show the spectrum coming from supernovae both in the early phase as well as the late phase. You see enormous differences in the spectrum between these two epochs. This also stresses that time domain observations are really important to understand supernovae. The last thing I focus on time domain astronomy is observing these peculiar objects called gamma ray bursts. They are the most powerful explosions in the sky, and they are basically flashes of gamma rays which last for few seconds in the sky, and these kind of flashes were known since in 1963, but however the results were not known out because this came as a surprise because people were trying to observe this gamma ray radiation as part of this nuclear test ban treaty in 1963. So, however, this kind of radiation was confirmed by subsequent missions, and these results later got published, and this is how the distribution of gamma ray burst looks like. And as I told you, these gamma ray bursts are a brief flash of gamma ray lasting typically few seconds, and thus this comes from an unpredictable region of the sky. And when people probed further, it was found that these sources emit enormous amount of radiation having power of around 10 power 52 Ergs only in gamma rays. So, these objects they show afterglow radiation in optical, X-ray, etc. So, what is shown on the top is the image obtained from a gamma ray burst at two different epochs. So, you can see these objects fade very fast, means these objects get dimmer very fast. So, therefore, to understand these objects we have to observe these objects as early as possible. Therefore, coordinated and timing observations are very important to understand the nature of these objects. So, what is shown here is the image of a typical gamma ray burst taken using the 2-meter Himalayan Chandra telescope. These gamma ray bursts are basically named as GRB 08. This corresponds to the gamma ray burst 080506. The first two numbers represents the year, the second two numbers represents the month, and the last two number represents the day. So, therefore, this gamma ray burst happened on 6th May 2008. So, here I show two images of the same region of the sky, one taken on 6th May and the other taken on 7th May. So, if you see, the object faded between 6th and 7th May. On 6th May observation it was visible, whereas on 7th May observation it was not visible. Therefore, to observe these transient events, high time resolution observations involving not only moderate size telescopes, larger telescopes are needed to understand these objects. So, this is how the light curve of a gamma ray burst look like, and as I told, high cadence observations are needed to understand these sources. So, here I list some of the Indian facilities which are available for optical and IR timing. So, we have in Kavalur many telescopes starting from 75 centimeter to 2.34 meter. We also have a Himalayan Chandra telescope which does optical imaging, IR imaging, optical spectroscopy as well as IR spectroscopy. In Nainital we have 1 meter telescope, we have a 1.3 meter. There is a new telescope coming up in Henley called the Growth facility. There is another telescope coming out in Henley called in Nainital Devasthal called the International Liquid Mirror Telescope project. We also have couple of telescopes in Mount Abu and a telescope in Giravali. So, these are moderate size telescopes which are very useful for timing observations. So, here I show some of the pictures of these telescopes. The left one is called the Vainapapu telescope. The second topmost, the second one on the topmost right is from the Mount Abu. The left lower one is from the Himalayan Chandra telescope, and there are 3 telescopes on the right. They are from Devasthal. Here one is the International Liquid Mirror telescope, one is the 1.3 meter, and the largest one is the 3.6 meter telescope. This is the currently largest telescope available in India, and these are some of the facilities or databases which are useful for time domain studies. The first one I point about GALAX. GALAX is the UV survey, a UV mission which scans the complete sky in 2 UV bands, far UV and near UV. So, this mission is now over. This provides an excellent database to probe or understand the celestial sources through timing. Then we have another database called IUE, International Ultraviolet Explorer, but this also has some amount of data wherein timing observations can be done. We have the Swift Ultraviolet Telescope in sky which can do timing observations. UVAT is the Indian facility. We also have the Catalina Real Time Transient Survey. This is a survey of the sky in V band. Lots of data is available to do timing observations. We also have the All Sky Automated Survey for supernovae. This also provides ample opportunity to find new transient sources. The Gaia mission is already up, providing lots of data. The WISE mission, Wide Field Infrared Survey Explorer, this has provided database in 4 infrared bands. This is also an ideal site to find transients. The large aperture cynetic survey telescope is coming, which will change the whole domain or whole thing of time domain astronomy. In the Indian context, if you see, we have the International Liquid Mirror telescope which is coming up in Devasthal. This also will provide enough scope to do timing observations, whereas many of the properties which I described in this talk will be a main focus of ILMT. So, to summarize, I would say timing studies is an excellent tool to understand the nature of unknown celestial sources. Find new types of sources such as AGN, planets. Time domain astronomy is an emerging area. Dedicated facilities are already existing and are planned. Simultaneous or near simultaneous timing observations over a wide range of wavelengths is essential and likely to be achievable. This will give a major breakthrough in understanding the nature of sources.